So with related rates, the idea here is you have something moving, you have a dynamic situation. You may have one rate that's changing, you might have two rates that are changing, you might have everything changing, you might have some things constant. So we're going to look for trying to identify, what's constant and what's variable in each problem. This acronym is going to help you to solve. This gives you, yeah, I know, isn't that funny? Yeah, dreads, I like that too. I don't know if that's how you spell it though, if it's dread. Is it dreads, is it ED or is it EA? How do you spell dread? EA? Dread. Dread. You're dreading this?
Or like dreadlocks.
Dreadlocks, that's what I'm thinking. That's what I was thinking. Okay, well this is dreads. So, D stands for diagram, so we're going to always draw a diagram. R stands for rates, so we're going to identify the rates in the problem. We're going to identify an equation that relates the things that are in the diagram. We're going to differentiate that equation, so we're going to find a derivative. And then we're going to substitute and solve. Okay? So let's start. We have, in the first example, a circular puddle of water. It's expanding at the rate of 16 inches squared per second. And we want to know at what rate is the radius expanding when the radius is 4 inches. So as we observed before, if the area of the circle is expanding at a constant rate, the radius is probably speeding up or slowing down. Which is it, Ian? This is your chapter. Yes, it's slowing down. Okay, so in any event, we agree that the rate of the radius changing is changing, okay? All right, so we have a circular puddle, so we'll start with D for diagram. And the circular puddle has a radius, so we'll put an R. And the particular point in time where we're interested in the rate of change of the radius with respect to time is when the radius is 4 inches. So I'm just going to label that radius 4 inches. All right, so there's a diagram. And then let's talk about the rates that we have. The first rate tells us that the water is expanding, or that the circular puddle of water is expanding at this rate. So that's a change in what? Change in area. Yeah, that's a change in area with respect to time. So I'm going to call that dA dt. I'm identifying, what the rates are. So I have dA dt equals 16 inches squared per second. And you can look to the units to help you with identifying the rates, if that helps. 16 inches squared would be an area, and area per second would be a change in area per unit time, so that kind of makes sense. Okay, and then it says, at what rate is the radius expanding? That's what we're looking for. So I'm going to call that dr dt. That's the rate we don't know. And I put a question mark there. So we've sort of summarized now what our rates are. So the next part of dreads is the equation. So what equation do you know for the area of a circle? Pi r squared. So we have area equals pi r squared. So there's our equation. And now we're going to take the derivative. Okay? We're going to take the derivative with respect to time because the area of the circle is a function of time and the radius of the circle is a function of time. Okay? So this is where our implicit differentiation comes into play. We're taking the derivative with respect to a variable that doesn't even appear to be in the equation, but it is because area is a function of time and radius is a function of time. So the derivative of a is just 1, but we have to multiply by dA dt, so the derivative of a is dA dt. Pi is just a constant, so I'm going to leave that there. The derivative of r squared is 2r, and now I have to multiply by dr dt because r is a function of t, okay, the derivative of the other function. So now I've done my diagram, I've done the rates, the equation, the derivative, so now we're ready to substitute and solve. Okay? So we'll substitute the rates. we know that dA dt is 16 inches squared per second. What's the matter?
Just realizing what's going on.
Oh, okay. So I have 16 inches squared per second. That equals pi times 2 times the radius. And so we're interested in the rate precisely when the radius hits 4 inches. Okay, at that instant in time. So I have 4 inches. And then that's multiplied by dr dt. So now all I really have to do is solve for dr dt. So I'll isolate dr dt by dividing both sides of the equation by 8 pi inches. So that gives me 16 inches squared per second divided by 8 pi inches. And now notice when we simplify that a little bit, the inches squared divided by inches just gives us inches.
And the 16 and the 2.
And the 16, yep, this divides out, we get a 2 here. So we have 2 inches per second, 2 over pi actually, 2 over pi inches per second. And we could calculate that, we could figure that out. Maybe I'll do that real quick. Let's take 2 and divide by pi. So I'm getting about 0.637. So that's about 0.637 inches per second. That's it. That's the rate. So,
There's gotta be something more.
so does anyone have a question about any of the parts of that, Brian?
The dA over dt, that's just the derivative of a, right?
You got it. Yep, derivative of a would be 1, and then multiply by dA dt because a is a function of t.
There's something step.
Say what?
There's something step and there's something.
No, the problems just get harder, right? I always start off. We start off pretty simply. Okay, sorry for that. Okay, so let's go to the next page. So flip your paper over. So that wasn't so bad. So we're doing, this is called successive approximations. Have you ever heard of that? You successively approximate the more challenging problem that you're trying to get to. You just keep taking baby steps so you can really leap. So we're getting ready to leap. All right. The next question. Each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area is exactly 16 centimeters squared? So, dreads. D is for diagram. All right, so here's our diagram. It says the side of the square is increasing at a rate of 6. So I'm going to call the side S. And what would I call the rate that the side is changing at? What's the calculus term for the rate? D what? DS. It's my initials actually. And Shearer dt. ds dt. Okay. All right. So ds dt equals 6 centimeters per second. Guess I jumped into the rates, didn't I? I should have stayed back with the diagram. All right. So the side. This is a side. This is a side. We know that the area is 16 centimeters squared. Area is 16. So what would that make the side equal to? 4. Okay, we might need that at some point. So, all right, so we finished our diagram. We got started on the rate. So there's the diagram, the rate, ds dt. We want to know at what rate is the area increasing. So what would that rate be called? dA dt. Good. Okay. So dA dt is what we're looking for. So we did diagram, rates, what's next? Equation, what's the equation? Area equals S squared, good. That's our equation. What comes next in dreads? Derive, so we're going to differentiate this. So we have dA dt equals 2s times ds dt. So derive Substitute and solve? Okay, so let's substitute. dA dt is what we're looking for, so we'll just leave that alone. And then we have 2 times the length of the side is 4 centimeters. And the rate of change of the side is 6 centimeters per second. I'm putting all these units in here so you can see that the units do work out. So that ends up being 848 centimeters squared per second. So we have a area, oops, just per second. We have an area per unit time, correct? Okay, how are we liking this so far? It's not so bad. So I would say half your homework is, as easy as these first 2 problems. Oh, you will. You will. Okay, so let's go to example 3. Let's try the next one. Successive approximations, guys. All right, now we have a calculus teacher perched on the top step. That's not a good idea. Of his 25-foot ladder. The ladder says right on. Have you ever been on the top step? It clearly says, warning, do not go above this. He's at the top step of his 25-foot ladder while painting the side of his house. He notices the ladder begins to slip. If the foot of the ladder is sliding away from the base of the wall at a rate of 15 feet per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? So when he's like, dude. All right. So we have the wall, we have the floor, and we have the ladder. So it's 7 feet from the ground. So I guess I should make it maybe kind of like that. All right. So here's my ladder, 25 feet in length. And the ladder is 7 feet off the ground. So we have 7 feet here. And we don't know this distance. Do you guys know Pythagorean triple that works here? 24, yep. So this is 24 feet. There's our little Pythagorean triple. Okay, so that's handy. We may need that. Anything else about the diagram? I think that's pretty much it. Okay, so let's go dreads. Diagram rates are next. And we are on problem 3. Okay, so the rates that we're going to identify are the foot of the ladder is sliding away from the wall at that rate. So the foot of the ladder is sliding away. So that means this part going that direction, 15 feet per second. I'm going to call this the x direction and this the y. So we'll call that x direction and that the y. So we'll say dx dt equals 15 feet per second. And then we want to know how fast is the top of the ladder sliding down the wall. So what would I call that rate? Awesome. Okay, so dy dt, and that's something I don't know. Okay, is that pretty much everything with rates? Okay, so now we have diagram, rate, equation. What equation do we use? Pythagorean formula, right? Pythagorean identity. So what do we have here? X squared plus y squared, right? The values x and y are changing throughout this whole problem. Agreed? Okay, how far down the wall is, and how far down the top of the ladder is, and how far away the bottom of the ladder. This is all dynamic. That was the picture we saw a minute ago. So that's all changing. So we have to include variables, x and y. If the length of the ladder was changing, we would have to call that z. But the length of the ladder is constant, right? So we can put that right into our equation. Anything that remains constant throughout the problem can just go right into the equation as a constant. So we have x squared plus y squared equals 25 squared. All right, now we're trying to solve for dy dt, so we need to differentiate in our next step. Differentiate with respect to t. So we have 2x times dx dt plus 2y times dy dt. That equals 625. Okay, so we did our equation, we did our derivative, and now we're going to substitute our values. So precisely when the ladder is 7 feet from the ground, the x value we said was 24, so we're going to use these two values. So we have 2 times our x value, 24, times our dx dt, which we said was 15. Did I lose you guys anywhere? No. You're okay? Okay, just tell me. All right, then plus 2 times y, which is 7, times dy dt, that's our unknown. That equals 625. All right, so now we're just going to solve for dy dt. So I'm going to bring all of this stuff to the other side of the equation. So I'm going to have 14 dy dt. That equals 625. Now I have to subtract. It looks like 30 times. We get 720 there. And then finally, our dy dt is going to be 625 minus 720, and then divide that by 14. So goof that. Divided by 14. I'm getting negative 6.786. Okay. What would the units be on that? Feet per second. Good. Now, what's up with the negative? Did I mess up something? It's falling, so what does that mean? It's going down. Yes. Oh, I did goof that. Oh, shoot. Yes, I goofed that.
Good thing I worked with pen.
Good thing I didn't. Okay, back to the drawing board. Yes. When we differentiate, oh, that totally makes a whole big difference. Okay, sorry guys. That makes a big difference. Okay. So the derivative of the 25 squared, that's going to be 0. So we have 0 here, 0 here. So we have 14 dy dt equals the negative 720. So it's just going to be negative 720 divided by 14. Oh, I'm so glad you pointed that out. Yeah, me too. I would have been too. Okay, so that gives us negative 51.429, and that is feet per second. Yeah, that's going pretty fast, isn't it?
How's it not
Yeah.
feet squared?
But I mean, he's 7 feet from the ground at that point. So
How's it not feet squared per second?
because it's a velocity, it's not the acceleration. It's at that instant in time when the ladder is 7 feet from the ground. What is the change in y with respect to t? That's change in position over change in time. That's velocity. So your units are going to be a linear divided by time. Okay, so we're looking at velocity there. Okay, let's do one more example. We have plenty of time here. So far, so good. Okay, example 4. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour. Oh, this is even harder. This year we did with the bearings and everything. Okay, so we're not doing it. What's that? We're not doing anything with bearings, but we are going to see sort of how they relate to each other. What's their distance? between them. So we have a ship right here. We'll call that ship A. What? Draw the ship? No, I'm terrible at drawing. What? Oh, did I have a little boat? There we go. Okay, that's ship A. All right, over here is ship B. He's got 2 sails. Okay. All right. The distance between them is 150 kilometers. Now this is a little tricky, what's happening here. Ship A is heading east at 35 kilometers per hour. So here's ship A going this way. And that's at 35 kilometers per hour. And then ship B is sailing north at 25 kilometers per hour. And that's 25 kilometers per hour. All right. How fast is the distance between the ships changing at 4 o'clock? So 4 hours later. So see if you can kind of envision this. I mean, you have, I'm going to draw this a little bit separate. Here's ship A, here's ship B. While ship A is traveling this direction, ship B is traveling this direction. So there's some distance between them, something like that. And then ship A continues to travel, and ship B continues to travel, and there's some distance between them. And ship A continues, and ship B continues, and there's some distance. Do you see how that's working? Okay. At every point, there's what shape? A triangle. Okay, so I think we can use a triangle to model this, right? It is here. It's all about you. Okay, so that just gives us a little bit of a diagram. All right. So let's use some variables. I usually label anything that's horizontal, I'll call that X, and I'll call vertical stuff Y, because I just think it's easy to think that way. So we'll call this our X distance, and we'll call this our Y distance. And then the distance between them, that's what we're going to call Z. So we have an X, Y, and Z. Now, you guys tell me which rates are constant and which rates are changing. Is this is traveling at a constant rate, right? Okay. This one's traveling at a constant rate, but this distance between them, is that a constant rate or a changing rate? That's going to be a changing rate, isn't it? Okay. All right. So I think we need to involve all 3 variables in our equation, because X has a rate, Y has a rate, and Z certainly has a rate. Okay. So what would be the equation to describe this situation? We just come up with the equation, the Pythagorean. Good. So we have x squared plus y squared equals z squared. And I guess before I get too far ahead, D is diagram, R is rates. We got these 2 rates, but it's the dz dt. That's what we're looking for. Okay. We want to be sure to keep that in mind. So we're looking for dz dt. Okay, so let's, we've got the equation, we've got the rates. What's next in dreads? Derive, right? So let's go ahead and derive. So we have 2x dx dt plus 2y, not yet, 2x dx dt, 2y dy dt, okay? And that equals 2z dt. Okay. Now I notice each term has a common factor of 2, so how about I just divide everything out by 2? That'll sort of be helpful. Get rid of all these 2's. All right, so now what I need to know is, I'm interested at the distance between the ships changing. I'm interested in knowing the distance between the ships, how that's changing at 4 o'clock p.m. So I kind of need to know where they are at 4 o'clock p.m., don't I? All right, so let's draw a little diagram here. This is going to represent 4 o'clock, and I don't really know exactly how that all looks. But 4 o'clock is 4 hours later. All right, so if this guy, if ship A was right here at noon, 4 hours later, he's traveled how far to the east? 140 miles, okay? And so now this dimension here is only going to be, this was 150. If he traveled 140, this is only 10 kilometers. You guys follow that? All right. Ship B started here. He's traveling 25 kilometers per hour. How far along is he 4 hours later? 100. So my diagram is certainly not to scale, but that's okay, because I'm just drawing a diagram. All right, so what is the distance here, this distance z? We need to calculate that, right? So we need like 10 squared plus 100 squared. And we need the square root of that. So I'm getting about 100.5. Okay? All right, so now I think we have everything we need. We have this x value. We have, this is the y value. We have the z value. We know what dx dt is, that's the rate. And we know what dy dt is, and we're solving for dz dt. So let's just plug in. So x is equal to 10. We'll multiply by dx dt, which was 35. Add to that our y value, which is 100, times dy dt, which is 25. That equals our z value, which is about 100.5. And multiply that by dz dt. Okay, so now we're ready to add everything up. So here we're going to have 350 plus 2,500, and then we're going to divide all that by 100.5. And that'll give us our rate dz dt. Okay, so dz dt is equal to 28.358. Anybody else confirm that?
No.
No? I have 350 plus 2,500 divided by 100.5. Anyone else confirm that? I think that's correct. Did you get that? Okay. Okay, so how about the units on that? What kind of units are we dealing with? Let's do a little bit of unit analysis. The 10 is kilometers. So we have kilometers times the 35, which is kilometers per hour. And we added that to kilometers times kilometers per hour. And then we divided by the 100.5.
Okay.
That was kilometers. So our answer is going to be kilometers per hour. Does that make sense for dz dt? Okay. So, not so bad? Yes, Brian?
Where did you get the 100.5 for the second time?
I just took 10 squared plus 100 squared, add them together, and take square root. Okay? A squared plus b squared equals c squared. All right. I'm going to stop this.